And thank you, Venus and Jasmine, for helping me throughout this project. And just thank you all for, being so welcoming and making this day in Daya so good. And without further ado, I wanna. Oh, is it gonna work? It is incredible. Okay.
You can go back to the slides. No, I think you have Zoom now opened. If you
Perfect. Without a further ado, let me welcome you to my talk, Real-Time CMB Using Machine Learning and Optimization of CMB and Class. What is CMB and Class? We will figure that out in due course. But first, I want to skip this slide and go to the next one because I want to talk to you about what Venus's project is and what the vision for this project is. So in Venus's project explanation, it's called Bringing Fundamental Constants to Everyday Life. And this is basically an outreach project where the ultimate goal is to be able to show some kind of physical simulation to the user so that they can interact with a made-up universe and change certain fundamental constants, such as the speed of light. You have this very beautiful representation of it here, but the ultimate goal is to use a VR headset where the user can go in and interact with this universe. And, this is just an outreach tool to make sure that we keep being funded, because most of the time, physics projects, they're not funded by people who actually do physics. So this kind of outreach tools, they're very important for us to, keep being able to do our research. But, unfortunately, the resources for this project are not so great that we can get a VR set set up in a full simulation. So we're going to keep it to this interface where you basically have these fundamental constants over here that you can vary, and 4 screens showing, in this case, a hydrogen atom, a planet, a galaxy, and what we're going to be talking about, the CMB. And you can change the fundamental constants and see how each of them changes and simulate new alternative universes, right? So this is our starting point. We have this picture of this concept, basically concept tool that we're going to build. But of course, building 4 simulations like this in 2 months' time is not really possible. So we're going to concentrate on only simulating one, right? And I decided to concentrate on the CMB because that's the one that I have the most interest in, because I don't know much about it and I came here to primarily learn new things. So let's focus on the CMB and let's ask ourselves, how does varying constants affect physical processes within the CMB? How does varying constants going to affect the surface of the CMB? We're going to learn which constants are interesting to vary in the first place, because, okay, I could look at this tool and see, okay, electron mass. Okay, I could vary that, but if there's no motivation behind that, then what's the point? We're going to try to determine which constants are interesting to vary in the first place. And in this process, hopefully, we also learn how is the CMB made, how can we simulate the CMB, and how can we make this simulation better? Coming soon. So let's begin by asking ourselves, okay, what is the CMB? And in the basic, most short terms, the CMB is the first possible snapshot that we have of the universe using electromagnetic waves. And why is that? Why is it the first possible snapshot using electromagnetic waves? Well, to answer this question, we have to go back a little bit, rewind a little bit, and go back to the universe right after the Big Bang, right? So the universe right after the Big Bang is this hot thermal plasma, this hot thermal bath that's very hot and very dense. And it's so hot and it's so dense, the temperature is so high that all particles in the standard model, they are essentially in thermal equilibrium with each other. You have very high energy processes that lead to very high energy particles being formed. You have all the elements of the standard model in thermal equilibrium with each other, and you also have a bunch of radiation. Basically, at this point, the universe is radiation dominated. Photons are basically breaking down the standard model particles. This is a hot bath in thermal equilibrium. As the universe expands, because we all know that the universe expands, the temperature of this hot thermal bath, it starts decreasing, and some of these very high energy processes, they start to become unavailable. So we can perfectly see this in this graph over here, where in the y-axis, this is the temperature of the universe. We see that it decreases, and in the y-axis, we have the degrees of freedom of the standard model particles, but we're gonna forget that degrees of freedom. We're gonna give it another interpretation. Just think of it as the percentage of high energy processes that happen during the universe, you know? So at the beginning, we have 100% of the particles in the standard model being produced and in thermal equilibrium in the bath. And as temperature decreases, we see that this line starts to decrease. And some of these particles, they start falling out of thermal equilibrium. We do not have, eventually the universe expands enough so that the temperature lowers, and high energy processes like the ones that would result in high energy particles like tau leptons, which actually stop at around 75.75 mega electron volts, they become unavailable, so they fall out of thermal equilibrium. And this process, it keeps going and it keeps going until something beautiful happens, which is that neutral hydrogen atoms start to form, and the expansion of the universe has made it so that the radiation, the photons that live in the thermal bath, their wavelength stretches and they become redshifted enough so that they do not directly ionize these neutral hydrogen atoms. So basically, the universe starts producing hydrogen atoms, and the radiation in the universe is not able to break them up anymore. We start seeing the formation of the matter that makes us all, right? As these hydrogen atoms start to form and the photons are not able to interact with it, the photons can now start traveling freely through the universe. Basically, here's a better representation of it. At the beginning, you have all of these protons and electrons scattering the photons around, and as neutral hydrogen starts to form, the photons still scatter a little bit, but lesser so, until at one point, at what's called the time of last scattering, where there's a lot of neutral hydrogen atoms forming, the photons are not able to interact with these hydrogens anymore. They do not interact with the free electrons and protons in the plasma, and they start permeating the universe. These are the photons that we observe when we look at the sky and we make an when we observe the CMB, right? These photons of the last scattering. So this is very important, understanding how the last scattering works, and we can actually make a statistical approximation of when the period of last scattering happened by solving something called the Saha equation, which I'm not going to go into details of, but basically we can more or less estimate that this happens when the universe is around 3000 Kelvin, which is more or less 380,000 years after the Big Bang. Good. So now we know what the CMB is and why is it the first possible snapshot or using electromagnetic waves, because before the photons were hitting each other and they were not traveling, we could not observe them. Now we can, and we can get a very clear picture of what happened of the sky of the universe at the time of last scattering. Good. So now let's ask ourselves, remember we're doing this to motivate something. So bear with me. Now let's ask ourselves, okay, what happens when we point a radio antenna to the sky and we basically observe that the CMB, that the energy of the photons that are hitting us from the CMB, on average, it's more or less the same. And we can use a Planck distribution to attribute a certain temperature to this. And we will see that the temperature of the now redshifted universe is around 2.7 Kelvin. However, we will see certain fluctuations of energies within these measurements that we're making, and they more or less fluctuate around 10 to the minus 5 Kelvin. These differences in temperature, we call them temperature anisotropies, and we can learn a lot from these temperature anisotropies. They are basically, they tell us a lot about the universe at the time of last scattering, because if we think about it, okay, the hotter regions in the CMB, the ones that we see, the hot spots that you see over there, they correspond to denser regions of matter at the time of last scattering. You have all this matter pulling gravity, basically pulling the thermal bath and pulling photons in, and essentially that makes them scatter more, increasing their energy. So when we make an observation, we see them as being hotter, and the colder regions of the CMB correspond to shallower gravitational wells where there's not a lot of mass. This basically gives us a very good understanding of the initial conditions of the universe at the time of last scattering. And if we study the CMB well enough, we could technically simulate how the distribution of matter of the universe as it evolves, right? So, okay, now we have a very good understanding of what the CMB is. Why is it useful? How can we start to make up a theory around it? So again, we look up to the sky and we see that we see these temperature anisotropies in a sphere. So naturally, we're going to define their delta t for a direction vector in a spherical surface. And because we're doing this in a spherical surface, we're measuring the CMB in a spherical surface, we're going to decompose this delta t in spherical harmonics. This is basically like taking a Fourier series in 1D, but we're using spherical harmonics. And assuming that the universe is isotropic and Gaussian, we will see that we can calculate the coefficients of the spherical harmonics solely using this CL. CL, which we call the angular power spectrum. CL is basically the holy grail of cosmology. And if the Planck experiment in 2018 actually went and made an observation of the sky, and by basically measuring the temperature anisotropies, they used spherical decomposition, and they calculated these coefficients for the spherical decomposition, and with it they calculated the angular power spectrum, and they came up with this beautiful curve, which if we smooth, we actually get the underlying curve that actually describes this. And if you're able to fit a curve through this, if you're able to go from the Big Bang and do a physical theory of the evolution of the universe and fit a curve through this observation, then you are on the route for a valid cosmological theory of the history of the universe. This is the holy grail. So let's try and do that. Let's try to simulate the universe. So we know that in the universe we have matter and radiation, and we have this angular power spectrum, which basically tells us about the differences in temperature in the sky. So let's think to ourselves, okay, what kind of effects could have contributed to these temperature fluctuations? Well, to see the temperature fluctuations that we currently see, then they are probably an evolution of the temperature fluctuations that happened at the time of last scattering. So let's ask ourselves, okay, what is responsible for these temperature fluctuations? Let's go back to the thermal bath. And we know that we have matter and radiation. And I explained already before that matter pulls the bath. But radiation, it doesn't want to pull. It basically creates pressure. It pushes this compression. This creates a tug-of-war in the thermal bath between gravity and radiation that basically creates pressure waves that permeate the bath. These pressure waves are called acoustic waves. That's why we see here velocity of sound in this particular interpretation of it. And at the time of last scattering, because photons and matter do not interact anymore, the oscillations freeze and we get the temperature fluctuations that we see in the CMB, right? So let's try to think about how can we model these acoustic waves? Whether or not the universe is matter dominated or radiation dominated at the time of creating these waves is obviously very important, because if there's a lot of matter, then the peaks of these waves are going to be great, as we have a lot of compression in the overdense regions of the thermal bath. But on the other hand, if the universe is radiation dominated before the time of last scattering, we get the opposite. These waves dampen out because of the pressure of the photons. If we write our metric for an expanding universe, which basically it's modeled like this, we model distances in an expanding universe with with the FLRW metric, but for here we have a time component and 3 spatial vector, and multiplying the spatial vector, we have this scalar factor over there, which basically drives the expansion of the universe. And if we use energy conservation, we will see that the densities of radiation and matter vary differently with the scalar factor. So why is that? And why is this important? Well, if we stretch radiation, we will get that it will stretch in the spatial components, but it will also stretch the wavelength. It will redshift. So that's why the density of the radiation changes with a to the power of -4, and meanwhile matter doesn't have a wavelength, so of course it changes with only the spatial components, a to the -3. What does this mean? Because the universe starts being radiation dominant and radiation changes much more rapid, radiation density changes much more rapidly than matter density, there will be at some point that there will be a crossover between radiation density and matter density, and essentially the universe will go from radiation dominant to being matter dominant, and the point at which they cross is called the matter radiation equality. Whether or not the radiation matter equality happens before or after the time of last scattering is also obviously very important, because it determines the peaks of this thermal fluctuation of these acoustic waves that I described before. Okay. So we know the universe has matter and radiation. Let's write the Friedmann equation, which basically tells you how the scalar factor evolves according to the total density. So let's plug in our current density, the 2 densities, and we're going to multiply it by the actual values for the baryonic matter and the radiation that Planck 2018 gave us. And let's write. In cosmology, we actually prefer to write the equation in that way, but we can evolve it anyways. So let's make a plot, put a line in the time of last scattering and see, and in the y-axis, let's put the fraction total density. So how the density of radiation evolves compared to the density of matter and radiation, and how the density of matter evolves compared to the radiation of compared with the density of radiation and matter. And we will see that in this particular universe, the radiation matter equality happens after the time of last scattering. We can use an actual simulator for the angular power spectrum to see whether or not this is correct. If this gives us a correct power spectrum, then we're on the way to model the universe. And if not, we have to try something else. We can use CMB, which I briefly mentioned at the beginning of this talk, to calculate the power spectrum, and we will see that our universe is trash. Basically, this black line is the Planck data that we want to fit, and the red line is what our model predicted. It's very bad. We have to consider something else. So what can we do? Okay, here the matter radiation equality happened after the time of last scattering. Let's try to make it happen before. And in order to do that, we're going to introduce a new more matter to the equation, right? So here it is. We introduced more matter. In this case, we called it CDM, stands for cold dark matter. And we're pushing the time of matter, the matter radiation equality before the time of last scattering. So that way, those gravity has enough potential to make those gravitational wells and pull the thermal bath. And if we make another simulation of our universe, we'll see that it's a lot better. Now we can actually fit the angular power spectrum. Okay, very good. But this is not the whole story yet. Can someone, okay, so here we have the derivative of the scalar factor in the y-axis and time in the x-axis. Can someone tell me what's wrong with this? Jasmine and Venus are not allowed to answer. No answers? Anybody trying to really wants to give it a go? No? No? Okay. I'll tell you the answer. In this universe, we have that the derivative of the scalar factor is decreasing. But we know, thanks to studying supernova, that the universe is not shrinking. It's expanding, and it's expanding at an accelerated rate. So this is wrong. There's something wrong with our equations. So how do we solve this? Okay, we have, by the way, this is our new matter term for cold dark matter that I added before. And we're gonna add a new term called omega lambda that's basically gonna be independent of A. And what this is the term that corresponds to dark energy. And with this, we will see that we get that the universe shrinks and then it goes back up again. So this is what we observe. Now we have an equation that we can use to model the universe. And in this process of coming up with this equation, we've learned a lot of things. We've learned how to simulate the CMB, how temperature anisotropies and at the time of last scattering affect the CMB. And we learned that we can use the power spectrum. And most importantly, we've learned that we've naturally come up with 4 constants that we can vary and that will have an intrinsic effect in the CMB. So now we're gonna go back to this project, and now we know a lot about the CMB. And what we're going to do is to change the CMB by varying dark energy, dark matter, baryonic matter, and radiation. Now, has this been done before? Yes, it has been done before. The Very Planck Consortium came up with this tool that you can use to do exactly that, which is a little disappointing, but it comes with its shortcomings. First of all, I would note there's no omega radiation. So we cannot vary radiation, okay? That's something that we can improve. Moreover, if you go to this website and use the tool and then inspect the website or go to the GitHub repository, you will see that all of the images here, they're pre-computed, which is not a very elegant solution. All of the images are pre-computed. That means that all of the combinations of dark matter, dark energy and normal matter in here, they're already pre-computed. That's all right. It works for this particular tool, but it's not a very elegant solution. But most importantly, it also limits the step size in which you can vary these sliders. If I were to go into this website, I'm not gonna do it now. Screw it. If I were to go into this website and vary one of the sliders, I will see that they only go in step size or a step size of 0.025. That's pretty bad. I like nice continuous sliders. So does Venus. So we're going to try to make a continuous slider and make essentially a real-time simulation of the CMB. So these are the cons that I already explained. The pros, it uses CAMP, which we have already learned how to use. So let's set up for our objectives. The project goal, to create a real-time CMB simulation, to enable dynamics for all cosmological components, baryons, cold dark matter, dark energy, and radiation, and then have continuous sliders because we like continuous sliders and because it's a much elegant solution. And we're gonna, the most important thing is that we're gonna compute the CMB power spectrum in real time. That's the real challenge here. Because if I were to do this project and try to put up a real-time simulation using CAMP, I will run into certain problems, which is that CAMP is a full-on cosmological analysis of all the cosmological processes that go on before the time of last scattering. And it works by evolving cosmological perturbations using perturbated general relativity. It requires of high accuracy numerical integrators. And this is basically very computationally intense. Between every simulation that you want to put up, you can get seconds or up to minutes to run one single simulation. So here is our problem. We need to learn how to optimize this in order to make a real-time simulation and in order to build our own tool. What can we do in order to do that? Let's use neural networks. Let's apply machine learning to this problem and let's highly optimize CMB to be able to do our computation in a matter of milliseconds and get this real-time simulation. So why neural networks? You've all seen pictures of neural networks at this point. There's no going around it, but as you can see, a neural network is just basically a bunch of inputs and neurons that are interconnected with each other. Okay, so what's going on here? In very basic terms, a neural network is a bunch of inputs that are multiplied by weighted matrices to end up with a desired output. Okay, so how can we use a neural network for our particular project? Okay, ideally, we will have a vector that includes our baryonic matter, our gamma, cold dark matter, and our, well, ultra relativistic radiation, which is also a component of radiation. In this case, we're assuming that the universe is flat, so we can actually calculate dark matter implicitly from these 4 values. But we basically have this vector that is multiplied by weighted matrices in a series of layers, and in the end, we get an output for our power spectrum. If you want more details about how this works, feel free to ask me at the end, but I'm gonna skip over the details and tell you about the advantages of using neural networks, which are basically that they can compute hard, complex, nonlinear functions, which is what we want to do here. Otherwise, we have to use numerical integrators that solve 300 ODEs that are coupled and they take a lot of compute. We want to reduce this problem to simple matrix multiplication, which is the real power of neural networks that we have found out for now in physics and computation, is that they greatly reduce the computation time by reducing the problem to simple matrix multiplication. And another advantage is that neural network frameworks, everybody's heard about them. They are very highly maintained. They are very highly researched. So all the programs that you can use, they are basically state of the art, and you're gonna get very fast runtimes and very fast training times. The only con is that it requires a very large data set to train. In order to train this neural network, we need to change the parameters of the weighted matrix according to some error. So what we're going to do is basically input our input vector of omegas into the neural network. Initially, we're going to get these weighted matrices at random. And at the end, we're going to come up with a random prediction. Initially, it's going to be random prediction of the power spectrum. And we're going to compare it to the actual value of the power spectrum to calculate an error. And with this error, we're going to tweak the weights in the matrices to better approximate the output. Again, if you want more details about this process, feel free to ask. But this is our algorithm that we're basically going to run. We're going to sample one of these omegas. H2 here is the reduced Planck constant. This is normally how we express, this is how we usually express the omegas. We're going to sample omegas randomly from this set of ranges. And then we're gonna calculate its power spectrum. We're gonna repeat this 80,000 times to create a nice large data set with omegas and their corresponding power spectrum. And we're going to train a model using this error. So for every run of the model, we're going to put in our input vector, get an output, and subtract it by the actual value of the power spectrum squared. And with this error, we're going to be able to tweak the matrices. Okay. So at this point yesterday, I was very confident that this had worked because I trained one model that worked with less than 1% error and that increased the velocity incredibly like increased the velocity by 300 times. And then I trained a second model that includes baryonic matter and cold dark matter. And it also worked incredibly well. So you can imagine my panic yesterday when I went to plot some graphs and we see that they are horrible. So basically, for some reason, once I added radiation into the equation and made predictions, I got these horrible lines. The dotted dashes are the predicted lines. And these two are the actual values for the angular power spectrum. This is horrible. And in fact, if you go around here, this is you cannot appreciate it, but basically that error is in the order of 100% error. So what the hell happened? What the hell happened, right? This is the question that I had this morning. And then I realized that I had problems with radiation this whole time. And I actually did a little bit of an analysis and went straight to the source. I looked at the temperature as calculated by Planck in 2018 and looked at the uncertainty of this temperature. And using the Planck distribution, I also calculated an uncertainty for the omega radiation for gamma. And basically, we have that this gamma is true for a magnitude of plus minus 10 to the power of minus 8. Before, when I was sampling, I was going well above this. So what I did is I checked again, I rerun the model, but instead of sampling from here, I sampled from the real value. I changed it to, I put an uncertainty of 10 to the minus 6. And I rerun the model, and thank God, it worked much better. As you can see now, the power spectrum is well calculated. The neural network is effectively learning the shape of the power spectrum. And here I have included a few examples. In this one, this is a very good approximation. We see it's 1.34% error and a maximum error of 3%. Here is the two plots, the subtraction of the two of them, and we see that the percentage error at each point is in the magnitude of 1 to less than 1 to around 1 and 2. So that's pretty good. In this other example, we have also that indeed the network has accurately predicted the power spectrum, but it doesn't do so well in the peaks, as we can observe there in this little points there, and in this one it's the same, right? And we can actually see that over there the error is maximum at around the peaks, and it tends to be minimum at around when the power spectrum goes down. So good. This is another example for much weirder cosmologies. We see that it does well. It normally oscillates between an error of 1 to 5%. That is not truly what you can achieve, and that's down to us. That's down to the fact that I trained the model with a much wider range of omega radiation. If I reduced the range of omega radiation to what I'm actually plotting here, I could probably get it to be consistently around 1%. So these are the results. Do you want to see? I'm now going to show you the actual tool. If Zoom lets me, that would be incredible. I'm just gonna cheat it. Take that soon. And this is the actual simulation of it. We see that we can plot the CMB, and if I change the values of the CMB, I have my amazing slider here, and it will change in real time. So I want to get this to be a seamless transition when I move the slider, but so far this is just a very early demo, and it only shows the image once after. But basically, this model, I actually have a plot here that I can show you. This is how the model does compared to actual camp. We see that it's a median of nearly 400 times faster. So I would call this model successful for what it's supposed to be. And that concludes the presentation. Questions? Yes.
I was wondering, in your last simulation there, you were moving one of the scales and
yeah, wait. Yeah. So this one or this?
No, the one you just showed with the different scales.
Yeah.
I was a bit confused when you were moving the top scale, the bottom scale.
Oh yeah, it moves, right? Okay, this is something that I forgot to mention. Do you have some chalkboard? Should I use pink again? No. Okay. So in a flat universe, you have that. I got it. B plus CDN plus this plus radiation. Radiation has two components, gamma and ultra relativistic. This has to equal 1, right? So basically, before I said we compute this explicitly from the others, because basically what this tells you is that initially you might think, okay, there's 4 degrees of freedom. There's actually only 3 because you have this relation. So you can calculate minus. Imagine I fuck up this formula like that. But yeah, so when I move this, it basically computes the last one.
And then why is the CMB like a square form?
Why is it flat? A very good question, actually. So I talked about spherical decomposition. It turns out that if you want to run an algorithm to put the power spectrum directly in a 2D representation of a 2-sphere, that algorithm takes, it's like complexity, it has this complexity. Can you see? It's like n to the 3, it's trash. It's very slow. It's very slow. So instead, what we do is look at the flat sky approximation, where instead of looking at the whole sky, you look at a tiny fraction of it, and you approximate it to be 1D. So instead of using spherical harmonic decomposition, you use Fourier transforms, and we have an algorithm called the fast Fourier transform, which is n log n, which is a lot faster. It works a lot better. More questions? Please give me questions. One more question.
So how big was the data set for you?
Sorry?
How big was the data set?
80,000 points. 80,000. I first trained a model with only baryonic matter, and that took 3,000. Then with cold dark matter and baryonic matter, 20,000 already did the job to bring the error down to 5% or something like that. I wanted to make sure that I got the error down to 5% or something, or less than 5%, ideally less than 1%. That's what you're aiming for with this kind of models. This was 80,000. 80,000 did the job, but again, the problem with my data set is that the radiation was too big. And actually, because we have a set value for the temperature of the universe and we can infer omega radiation for that, the models that we use, they are very dependent on this value. So if you're trying to make a data set that has a wide range of omega radiation, you're gonna have it's a nightmare because it crashes. So imagine I run some code and it's run 40,000 simulations and suddenly it crashes. And you're like, okay, at least I have 40,000 data sets that I can use. And you go to open the data set, and on top of that, it's crashed and it's corrupted. So it's useless. So basically, you have like 2, 3, or even 8 hours of computation that are lost. Getting this radiation down was definitely the hardest part of this project. Yeah.
Maybe you can collaborate with those guys. They have like supercomputer or something.
For camp, maybe, yeah, maybe and actually it would be good to have a computer with a graphics card, because training these models for a data set that's 80,000, it takes around 20 minutes to run one model. When you're training this kind of models, I'm just gonna go on tangents if you allow me, so stop me when you, but when you're running these models, sometimes it's a little bit hard to determine which parameters work best. So what you do is you create an ensemble of possible parameters and you run several models and you pick the best one. So yeah, 80,000. That's the question. Yes?
It'd be nice to compute a different equation of state for that energy.
Yes?
So it's based to put in not just a constant between the density and pressure for cosmological constant. Could put in some dependence on A.
Yes. So for this particular model.
Yes.
Okay. So I like that you asked this question.
The gap energy also has a gap pressure component. There's an equation of state that relates the two of them, and it's usually used. What it is that take the density to the positive. Pressure is minus the density. But you don't need to have, you could put in a slight variation of that. Which it should be relatively easy when you correspond to put in an A to some exponent which is very close to 0.
Yeah. Well, I'll tell you why for this particular model, I would find it a little bit difficult. So at the beginning of the presentation, I actually said an optimization of CMB and class. We've talked a lot about CMB, but I haven't talked much about class. It's because in the end, class is another simulator for the angular power spectrum. And class, I haven't gone into the details, but it essentially allows you to add variations in these constants. And it would be possible to do so, but in this model, which is basically, this depends on CMB. And the truth is that neural networks, they're very nice, they're very fast, and they're very precise, but they're so far we struggle to understand whether or not we can go beyond the model that we've trained this in. So you can't. Yeah, exactly. It goes back to the question of, okay, is this artificial intelligence or assisted intelligence? In this case, I think this is a perfect example of assisted intelligence because you're just optimizing a problem. But CMB, as far as I'm concerned, I could be wrong, does not allow you to make simulations with different, with variable dark energy. Yes. Yeah, yeah.
I was wondering if other people have made neural networks trying to do the same thing.
Yes, yes. Other people have done that, and this project is called Cosmo Power. Do not ask me who wrote the paper, but if you look up Cosmo Power, you will see that they actually have done exactly this, but they did not vary radiation. They buried, once you go into the Planck paper, they have a table with 6 parameters and their uncertainties, they made it so it can vary those 6 parameters, but not necessarily radiation. Yesterday, I figured out why that is. The advantages of this model are that the bounds of baryonic matter, cold dark matter, are bigger than the ones in Cosmo power. We allow for radiation to vary, and with using photons and ultra relativistic particles, which I kind of have ignored for this particular explanation, but we have those 4 degrees of freedom, which 2 of them they do not have in Cosmo power, and the ranges of these degrees are much bigger than the ones in Cosmo power. So this is not necessarily a big improvement from Cosmo power, but it does include additional features that could potentially, that if you made a unified model of the 2, if you were to do a model of the 2, then it would probably be better for this kind of application. Vinos? Of course, talking to my amazing supervisor. I can tell you that the part I enjoyed the least is doing the data set. The part I enjoyed the most, probably coming back and running the model, plotting and seeing these images. These images with that on top, it's good. And once you actually get this simulation running and you see that, okay, it works more or less like the one in Planck, it's good. You know, I felt like I was improving something. Something else? No? Thank you.
Okay, so with this our today's session is concluded. Let's also maybe thanks to all speakers today.
Yes.
Not done yet, so we will have a group photo downstairs. All right.
And then at 6 p.m.